True. So we got a good turnout today.
Oh yeah. All the Brady Bunches here.
Yes. Excellent. Well, Joe, you want to kick us off with intros? You're the first square in the Brady Bunch I see.
I'm Joe Capriati. I was worked as a UBC for a while, postdoc, focused on SimPEG development. Now I'm down at Mines as a research associate. Still involved with SimPEG as much as I can. So I still kind of, doing a bunch of pull request reviews when I can and going in there. So interacted with you a bit on there, on your pull request that you already put in. Yeah.
Awesome. Doug, I see you next.
Oh, hi, I'm Doug Oldenburg. Matt, nice to meet you. I think I know most everybody else here. So I'm professor emeritus at UBC in geophysics.
Excellent. Deb?
Yeah, my name is Devin Cowan. Nice to meet you, Matt. Yeah, I wear a lot of hats. I'm doing SimPEG development. One of the things I'm active in is trying to build up all the user tutorials, make it a little bit easier for new users. Spending a lot of my time right now working on some of these new natural source systems like QAMT and MobileMT, and then also some plate modeling and how we are going to do that for time domain problems, working with tetrahedral meshes and that kind of stuff. So a little bit all over the place.
Excellent. Thibaut, I know you know everybody, but if you want to say anything.
Yeah, so Thibaut, data scientist and geophysicist with Cobalt, so working with Matt, and I'm very happy to see all his very dedicated work at all levels with PyMath solvers getting pushed to the open source.
Awesome. Santi?
Hi, I'm Santi from Argentina. I'm actually working as a postdoc in UBC in Liz's group. And besides the research I'm doing, I develop open source software. I'm involved in Fatiando Terra and also contributing with SimPEG mainly the last year. So yeah, nice to meet you.
Dom?
Hello, I'm Dom. I'm in Vancouver. We used to be at UBC too. Now at Mirage Science as a scientific programmer, and I'm all over whatever code improvement we can do to SimPEG.
Yeah, you're the main architect behind the GeoApps, right? Or is somebody else behind that now?
If you know what the GeoApps are, then yeah, most people don't care, but yeah.
Oh.
So, Kaylin? Kaylin, you're muted. There we go.
Hi, Kaylin Martins. Thanks, Lindsay. I work for SJ Geophysics. At our company, we're interested in doing large loop EM and MT for starters at least, and IP inversions. So that's why we're interested in SimPEG.
Awesome. Matt?
Yeah, so I'm Matt Plume, a software engineer at Cobalt Metals, and I work with Thibaut. And I've been, in addition to a lot of the kind of machine learning work that I've been doing, I do a lot with our compute infrastructure, so trying to make things faster. And so a lot of the work that I've ended up doing lately has been with accelerating our geophysical inversions and trying to figure out various ways to support various architectures as well as making the inversions run as fast as possible.
Well, thrilled to have you here. I'm Lindsay Hagee. I'm an assistant professor at UBC and been involved in SimPEG for quite a while at this point. But yeah, I mean, so normally we start, I don't know if anybody has any quick announcements or things to bring up for the group, and then we can perhaps hand the floor over to Matt. Announcements going once?
I mean, I maybe have like one thing I'll want to ask while he's here, but it can wait till afterwards.
Okay. Sounds good. I think only quick things is Dom BCGS is tomorrow. That's right.
Still happening, yeah.
Still
4:30.
Excellent. And then John Cudeye will be pinging some of you for newsletter updates, because we'd like to get that out in the next week or so. So please get back to him if there's anything you'd like to share in that, and feel free to ping if there's things you would like to include, like a new pull request with MUMPS. So Matt, yeah, please take it away.
Certainly. I have some material I can share here. I'll go ahead and share my screen. Looks like got participant screen sharing is disabled.
Right, Joe, are you gonna do that, or you want me to do it? Last time we both did it.
I got it.
Okay, thank you. Okay, I think you should be able to now.
Yep, looks like it's working. All right, so the first thing that I'd like to share here, so I have a set of benchmarks that I've run recently. We do a lot of work in the cloud. We run on AWS, and Thibaut put together a small forward simulation benchmark for us to be sort of comparing performance across instance types. And so I just wanted to show some of the variability of performance across instance types, as well as the effects of solver ops. And so we can see here, we've got our baseline Paradiso with, as part of MKL. And then we have the MUMPS solver that we've been using at Kobold for probably the last year or so, as we've been using our M1 and other Apple Silicon machines. And so the MUMPS software right now is not as performant as Paradiso, at least in cloud usage. But it has allowed us to do local development on M1 laptops. And in a second, I'll show some benchmarks also run on my M1. And so we can see here that the solver ops, if we're hinting to either Paradiso or MUMPS that we are dealing with a symmetric or SPD matrix, that we see significant performance increases in both cases. The MUMPS pull request that I have up right now standardizes the attributes across both of these solvers so that you can specify the same solver ops for both of these, as well as standardizing the behavior of those solver ops. So previously, when you were hinting to the MUMPS solver that a symmetric matrix was in use, it was actually treating that matrix as Hermitian. And that's different from the way that our other solvers are working. I also have in the MUMPS PR the capability to deal with Hermitian matrices, but that's through additional means where in SciPy's sparse matrices, there's the .t attribute, which is a transpose, and then there's the .conjugate method, which allows you to take the complex conjugate. And so .t.conjugate is how to deal with that kind of stuff.
Matt, one just quick question, or things happening in the chat might be, Joe, do you want to just jump in and ask your question? Joe, you're muted.
Yeah, these are all timings. So I don't have info.
I didn't want to interrupt you too much, sir.
Oh, sorry. Yeah,
I'm also curious about, like I said, the memory requirements between the two of them.
I haven't looked at memory requirements differences at this point. All of these, or this benchmark is very small and fits very easily into an 8 gig instance. So I haven't looked in detail. The thing that has been kind of most of a priority for us at this point is decreasing the simulation time. If we need to we need to up the memory, we can generally use a larger instance up to a certain limit. At which point, I think there's going to be out of core kind of stuff that we would need to be doing. But that's not something that we've looked at.
One other question, you said you've been doing stuff with M1 processors as well.
Yes.
Did you run any simulate or any timings on using Apple's emulation stuff, right? Because they have you can also do like emulation for like 64 processes, right?
Yeah.
With the timings, like how much that slows it down versus using something native. Just out of curiosity.
Yeah, I don't have quantitative numbers for this. I do have qualitative painful. It was not a great experience trying to run Party, or even doing things like building the image. We ensure environment reproducibility by running inside Docker containers. And even building the image for that was significantly slower. So I didn't bother to do that just because of things that are not as computationally taxing being pretty painful to do. The MUMPS numbers on my M1 and the laptop that I'm using here, we can see I've got a MacBook Pro 16-inch 2021. It's the M1 Pro system. Our numbers are looking pretty solid here. And they're actually better than some of these. Where did it go? There we go. Better than some of these numbers that we were seeing in the cloud. These cloud numbers are also hobbled at this point by a Dask related issue. So the environment management for all of those numbers, I ran using basically these spin up Dask clusters under the hood. And it seems like when Dask is involved at this point, things run slower with both Pardiso and MUMPS. But this was not an issue that I could reproduce with the Super LU solver. So that's an open problem for us. And we would see significant performance increases as well, probably on the order of between 25 to 50% if we can get that problem solved. So taking a look at these numbers here, we're seeing this is actually pretty similar to what we would be seeing on a local Apple Intel machine. I think I've got an i9 here. So it does pretty well. And we can also see that supplying various hints to this simulation increases performance. So I want to really make these hints kind of standard and also available.
And just to make sure, Matt, so the runtimes that you have on the cloud, yeah, is like an Azure machines or something. Those are not Apple M1
no
cores,
so these
right?
the instance architecture here, so these are x86 64. So for example, an R6A is an R6, so R is memory optimized AWS instances. It's a 6th generation and it's an AMD processor.
Got it.
The ARM processors here are AWS's Graviton processors. So images that are built for those will work with the M1 as well.
So all these numbers could potentially be different if you were to test it on M1s.
Yeah, so these numbers are different on M1s. So these are running with this sort of Dask orchestration layer in between. Looking at M1 here, so we've got the three numbers that we were looking at are unsymmetric, symmetric, and SPD. And we can see here that the corresponding numbers on M1, unsymmetric, we've got, and then symmetric and symmetric positive definite. But I would expect that these numbers will go down as we deal with that Dask related issue, which I have not been able to chase down. as far as the kind of, so this is the effect of the changes, is making it possible to run MUMPS in a standardized way, on instances where we can already run Partiso, but also extending our capability to ARM instances, standardizing the interface between the two so that the same solver ops can be used. There's kind of two different sets of changes. One of them is ready for review, which is what's in this PR. And then the next one is not ready for review. And that's, how do we package this properly? So right now, PyMat solver, as it stands, we'll take a look at the main branch here. We have this MUMPS interface that's slightly shimmed out. This interface works, and we've been using it at Cobalt for the last year or so. It's something that could use some love and care, and that's what I've done here. But then kind of the next step after this, and Joe and I were discussing this kind of next step in some of the PR comments here, is how do we make this available? And it seems like there are a couple of different problems that we would want to solve. So right now we have a Fortran interface, and that's something that's going to get kind of tricky to support, especially with the deprecation and removal of disutils. There's some complications with NumPy disutils, which is the standard way that F2Py extensions get built. And so F2Py is a tool that's used to take this kind of Fortran interface here and make it into something that Python can understand. MUMPS also has a C interface, and Python is a great way to write Python code that needs to talk to C. PyDiso already does this, and a Python extension is probably going to be the future here. So porting this MUMPS interface to Python, that could live inside PyMat solver, or it could be broken out into something like PyDiso. I think that what we have right here as far as this packaging, this is how to package things with F2Py. This is not ready for release here. This is in a branch on my fork here, Cobalt Metals PyMat solver. This is good enough for our use at Cobalt Metals because we have very tight control over our environment. But what ends up happening with this branch, and why this is not included with these changes here, is this branch modifies PyMat solver in such a way that if MUMPS was not available on your system, PyMat solver could not be installed. That's not releasable. That's great for us, and it leads to this kind of benchmarking capability and really solid results on F1. But this would be the next step of going, okay, we've got some love and care applied to MUMPS, leaving the packaging status quo as it is, where someone would need to kind of DIY the installation. The next step would be taking this packaging capability and making it into something that we can release to the world as this is how to use PyMat solver and have MUMPS available. It would be great to be able to interface with the version of MUMPS on Conda. That would be, con install MUMPS, con install PyMat solver, and you're good to go. There might be an intermediate package that we would do where we would have, I don't know what it would be called. It would be some sort of MUMPS interface. I'm hesitant to try to do anything with the existing kind of open source MUMPS interfaces because they've been dormant for so long, and because our MUMPS interface needs are so limited. There's very little that we actually need to do, so we don't need a general purpose interface to all of MUMPS capabilities. We can get feature parity with PyDSO with a very, very small amount of glue code. So we could do that MUMPS interface ourselves and maintain that in the same way that PyDSO is maintained. That's probably the most pragmatic way to do it. And if someone decides later that they write an excellent and well-maintained MUMPS interface, we can then transition to that.
Yeah, that's kind of my thoughts on that as well. So it's probably the best route. That way we can kind of keep it like how you're saying, like it's kind of hard to build PyMat solver with MUMPS at the same time and have it being an optional thing. Are you guys using, so you're talking about the PyDSO stuff, have you guys been using that like built locally on your own systems? Have you been just installing it through CondaForge? What have you guys been doing?
We've actually been pip installing it.
Okay.
That's worked really well for us.
Glad to hear that. It's interesting. So yeah, I think that'd probably be a great way to go about that, honestly. I've been definitely interested in MUMPS stuff for a while, that just haven't had the time to sit down and play with it because I should probably have a little bit more time coming up soon. I'm supposed to be getting a new Apple Silicon process machine, so I'll have a used to doing this. And I think I already also mentioned on there that I had already played around a little bit in my own computer with the Apple solvers as well. Not sure if you ever got a chance to do that.
No, I looked at the fact that they can't do complex, and I was just like, no, I'm going to stay away. I have looked at, I did look at UMF-Pack as a potential other sparse solver, but the performance that I was getting was nowhere near MUMPS.
Interesting. Yeah, so it's like, there's a few things. Did you try any of the, like specifically the CholMod solvers?
I have them on my radar, but I have not tried them. The really nice thing with UMF-Pack was there's a package called Scikit UMF-Pack, and I just wrap direct UMF-Pack, and I had a solver that I could use. So the wrap direct stuff that lives in solvers.py here, that stuff works. And it made it very quick to try UMF-Pack. Unfortunately, the results were not great. So I was really happy that it was so easy to wrap that solver. Someone else had a nice interface that made that pretty cool too.
Yeah, there's a good CholMod, so like Scikit sparse, I think, that interfaces with CholMod pretty well. I mean, part of that means you can only do, Cholesky factorizations, but those are pretty fast things to do, as you see from like just taking advantage of that is symmetric, is positive definite on the solvers there. I've I've looked into a bunch of different solvers myself, and it's just like, okay, well, most of the things that we were doing for DSO was working pretty well, but now that we're moving on to other stuff, it definitely makes sense to start getting back into these other solvers.
Yeah, having something that's available on more architectures and is reasonably performant is huge, and it seems like MUMPS does that pretty well.
Yeah, I think the only issue with MUMPS is that it's not as easily installable on Windows. Like you can't get all the features on Windows. Like I don't think there's an MPI, and you can't do a bunch of the reordering heuristics on Windows.
Yeah,
but it works. It still works.
Yeah, and I'm thinking if you're on Windows, you're probably at this point anyway on an Intel machine, and PyDSO does pretty well.
Yeah.
So.
and it's still worth mentioning that your PR maths brings in the possibility to pass option to the solvers, and that's how you also improve the Paradiso performance. It's not only a PR or MUMPS, but bringing in those options. You were showing good, like it's improved both the Paradiso and the MUMPS side.
So that's not quite it. So the options that you could pass to Paradiso previously that is symmetric and is positive definite, they worked differently for the MUMPS solver. And so now what you can do is taking a look at the benchmark itself. We can read this benchmark code. We can see here that, okay, which solver do you want? And so now, if solver is Paradiso or if solver is MUMPS, we import the correct thing, but then we don't have to use different solver options for different solvers. And the solver option behavior is also standardized. So symmetric now means the same thing for Paradiso as it does for MUMPS.
One of the things that I'd like to do, or we should probably put up a issue on SimPEG itself, is to make use of these flags in more of the simulations than they are, at least by setting them default flags for some of these things, because most of the systems that we do, we should know whether they're positive definite or symmetric. I don't think that is advantage of in many of the systems, actually. I think it's only really taken care of in the DC simulations.
Yeah, like for most are, and as I said, we've already switched us to that branch of PyMath solver. So I'm actually using, it's very nice with the solvers too, that you can set the solver option on the simulation object. So it's just like a simulation.solver option, and you specify that it's symmetric and positive definite. And with that single line of code in SimPEG, you end up with 15-20% speed increase, which is very nice.
Oh yeah. My point is that we should know some of those things about those systems. There should be no reason that you would have to set that as a user to know.
Yeah.
Hit these flags, it's going to make it go faster, right?
And 100% that we should go at some point as default within the SimPEG simulation object. But I just wanted to emphasize that it's a one-liner.
Yeah, it would be awesome to, step one, standardize the options, and then step two, get the options in by default. That would, if someone just have stuff running 20% faster with no code changes just by upgrading SimPEG, make a lot of people pretty happy. We've had simulations that run for 5 days, and the effect of that is 5 days down to 4. That's pretty substantial.
So you said you're having some issues with Dask stuff as well. What?
Yeah.
Can you give the context with what you were using Dask to do? And
so one thing that we're doing right now is we're running a lot of simulations. We're running an ensemble of simulations, and then we would run simulations across a lot of machines. And what I've found, and this is very, very confusing for me, is that if I have a piece of code that let's say I break this simulation out into simulation.py, and then I have a piece of code that either runs starts up a DAS cluster and then submits this simulation function to that DAS cluster. I see the simulation run slower there. I also see the simulation run slower if I create a DAS cluster, do absolutely nothing with it, and then do a sub-process run of a simulation.py that just has the simulation in it. It's no, that should have absolutely no awareness of the DAS cluster. It's a very deeply confusing issue for me. But it's reproducible.
Interesting.
and I tried reproducing it. It's reproducible with both the Paradiso and MUMPS solvers. I took a simulation and vastly reduced the number of time steps in it, and tried reproducing it with the Super LU solver just to see if I could have something minimum reproducible that I could send to somebody else. Like, hey, you don't have to install this software. You can install SimPEG and then off you go with this reproducer. I couldn't reproduce it that way. So I sort of said, I'll leave that one for later. But it is a problem that we're aware of at this point.
Interesting. It's like that, yeah. There should, like in those cases, you're not doing any sort of communication, right? You're just
No, it's an idle DAS cluster. It's just sitting there. So it's, yeah, I don't understand why it's happening. I'd love to get to the bottom of it, but I
so
haven't
you're
had
starting up.
time to explore.
You're starting up a DAS cluster. There's a master or a whatever they're called, the
Client
not the client, the thing that controls the clients, like the
scheduler.
Sure, there's a scheduler. But there's a thread that has, like, say it's running on the main machine, and then when you start up a distribution or like a bunch of DAS clusters, there's one that specifically manages everything else, and then there's all the other clients. Sometimes, like, the main thread can be a client as well.
Give me 1 second and I will pull up the code that has this problem.
Is Super LU, where is Super LU coming from?
Super LU is one of the wrapped solvers. It's the SciPy sparse solver.
And I don't think it's parallel, is it?
No, it's pretty bad.
Yeah. It's multi-threaded. Multi-threaded Super LU. Okay.
Yeah, I was, so in the meantime, I've definitely been looking at a bunch of MUMP stuff and seeing where they're at. So the Conda Forge, the one that's available is 5.2.1. And I know they've been trying to update it to more recent versions, but it's been struggling on Conda Forge. There are a few pull requests on the feedstock to update it to more recent versions, but none of them have passed. So there's like a MUMPS MPI, there's a MUMPS sequential. There's those two kind of packages. So,
yeah. It was interesting. So we updated from 5.5 to 5.6 recently. There's a really nice CMake set of CMake files called SciVision/MUMPS. And that has been very, very useful for getting MUMPS compiled and built with various options. The options changed a little bit from 5.5 to 5.6. So that was sort of tedious.
Yeah,
so
I saw that they added support for 64-bit integers or something.
Yeah. All of the work that we've been doing has been with the sequential MUMPS, which sequential is not the greatest name because it is multi-threaded. It uses both OpenBLAS and OpenMP threading. It just doesn't run MPI. And that gives us feature parity with Paradiso. Now it would be really nice if we could improve kind of that single threaded performance as much as possible, because if we throw more machines at something, then that the cost just balloons in order to run stuff. So efficiency in the kind of single threaded case has been something that we've been trying to pay attention to.
Well, this is really exciting, Matt. As you can see, I was kind of laughing as you pulled up the MUMPS, the Fortran code, and you can see in Git it's 7 years ago. It was last touch. So I'm really excited you're pushing on this. I guess I know you've been chatting a bit with Joe on the pull request. What do you both sort of see as next steps here?
Well, in like looking at the pull request, I'm happy to take that in. So at least if somebody can, you know, get MUMPS working, if somebody can install it, like the option is still there. And I see what you've done with the pull request. It looks good. So as far as bringing out the feature parity. So if someone can install it with that bare bones interface that's there right now, that's fine. We can figure out distribution and how to do all those other steps, I think, later, but that's kind of what I see.
Yeah, that sounds awesome, because it's like the makefile stuff, you know, the building the MUMPS interface and then renaming the init. We've been doing that for a year and it works great, at least in our use case. It doesn't look like writing the Python will be that difficult, especially with the precedence of PyDiso and then a couple of the other MUMPS interfaces. It's like there's some annoying C versus Fortran things of like there's IControl thing and they're 1 base versus 0 base. So MUMPS says, hey, define these macros and you'll define them. So it looks a little tedious. One of the things that I did was I moved that conjugate option that was in Fortran out to a NumPy conjugate call to reduce the amount of C kind of stuff that we would need to do. So I think it's going to be a fairly tedious but not difficult write. And then the really nice thing that I think that we can do is, you know, using setup tools. We would have the option, if we so choose, of you know, including that MUMPS interface either in PyMath Solver as an optional extension, so that if compilation fails, the extension or the package continues to install without the optional extension, or we can break that out. I would be happy to do either way, whichever one is easier. I'm just wondering about, you know, integration kind of stuff of, you know, how straightforward is it to do the kind of integration testing of all of the pieces and have someone be, you know, have really high assurance that the MUMPS extension is working. That would be one argument in favor of keeping it in there. But we can look at other options as well.
I know it's Santi or Joe, if you've got thoughts on if it should be included or not, or where we perhaps start and then figure out that question later.
I made yes, go ahead.
My first thought is to kind of treat it the same way we treat the PyDiso interface. Just because it's like, okay, well, if you want that, you can install that and get those things available to you separately from PyMath Solver or PyMath Solver. I know it's just like another level, but it's kind of a unifying thing where those specific things are separated. It gets, as soon as you start trying to include compiled code inside something, especially optionally compiled code, it gets rather tedious and complicated. So if we could just not.
Yeah, and then the question becomes, you know, how do you do binary distributions versus source distributions? And if you're doing a separate binary distribution, it probably gives you a lot more flexibility. Yeah, I'd be fine with another package.
Is that something that would be useful to start in the SimPEG organization like sooner than later? Or I mean, I know, Matt, you've already got some code where you're playing around with this. What are your thoughts on that?
I think it'd be great to at least stub out a repository for that. And then we can see about populating that repository later. But if the stub is there, then I think it would be a matter of submitting PRs to that stub. So get the infrastructure in place, sort of in a minimal way that makes it easy to contribute. Because it sounds like, Joe, you might have some time coming up soon. I might have some time coming up soon. But if we've got the place for it, then it's one fewer thing that we would need to do, and it would probably be pretty quick to at least set the place up.
Yeah, and hopefully it shouldn't be too hard to create that interface. Like I know I did the PyDeso stuff in a few weeks, like here and there, so it wasn't that involved.
No, I don't think it'll be terrible.
Like I just haven't had the need to do it yet. I've been interested in doing it.
Yeah.
I'll probably have the need to do it soon, and as well as like put up the an interface for the Apple solvers as well when they're useful.
So an important question is, we'll need a name for it.
Yeah, a name that's not MumPy or PyMumps.
Yeah.
Or MUMPS. That's the first thing that I was thinking. That's a terrible name.
MUMPS DSO. Well, it's like it's PyDeso because it's ParDeso.
Because of party, so yeah.
Yes. Well, maybe we can start an issue and brainstorm some names.
Well, if it'd be appropriate as like a sidekit, I don't know. Yeah, well, we'll think about it.
That sounds good. Do other folks have questions for Matt, or kind of more broadly thinking about?
Yeah, I have something that's maybe somewhat related. So, I mean, I'm also working on large loop time domain EM stuff. I'm also wanting to implement the B field. I'm currently working on solving this problem on a tetrahedral mesh. And I'm putting conductances on the faces so that you can do plate light structures. So I'm not sure if Thibaut's mentioned, but we're working on some very similar problems. And one of the issues that I have, do you mind if I screen share? It's a little bit of math, but it should be okay. And it sort of comes up if you wanted to use the B formulation on a tetrahedral mesh. This is the system that you have to solve at each time step. And you end up having in your system the inverse of one of these mass matrices. And when you have a mesh that's like a tensor mesh or a tree mesh, this is diagonal, so taking the inverse of it is trivial. If you have an unstructured mesh, it's no longer diagonal. And so it's, in a way, it's kind of like you have to do a solve within your solve. And I'm sort of just kind of looking for ways that I'm going to attack this. Like, can you define this using the ParDeso solver and then define A using a ParDeso solver in sort of a nested way and have it work out? These kinds of things.
So my recommendation, Devin, is to avoid doing those inverses, because those inverses are actually dense matrices. Yeah. So if you tried to actually form A using that ParDeso solver, it would be.
I don't want to like solve it and then send it to dense and then like actually store it outside of that. I mean, I'm just starting to look at this problem today, but
yeah, like
you want to use anisotropy or you want to put it on an unstructured mesh. This is an issue.
My recommendation would be if there's a way to not use the B solver, like if there's a way to not use the B formulation.
Yeah, well, if you're going to, at least for what I'm doing, if you're going to model dBdt, then you use the E formulation, no problem. If you want to solve in terms of the magnetic fields, then I mean, I haven't looked at the H formulation, and maybe you can use that for not having conductances, but if you have a conductance, you're kind of stuck with E on edges and B on faces, and you wind up with this.
I think a better route, if you wanted to get the B field, would be to implement the integration part on the E field measurement to do what you want to do.
Yeah, I'm not the biggest fan of that one, but
It's something we should try, though. I mean, we should have the option to at least have a sense of what the accuracy is, and you know, there might be a lot of settings where that works just fine.
okay. Yeah, but even if it resulted in storing two dense matrices, even if you didn't want to do it, but could you still do it with the machinery that we have?
So that, like the A matrix you would form. So, okay. If you want to form the A matrix for those tetrahedral meshes using that inverse mass matrix, it is going to be dense. Like there's no way you can get around it because of
Oh, okay. Right, because you have the inverse of that mass matrix, which is a dense matrix, and then you're now trying to go and factor something that's very dense, which the benefit of the whole thing was factoring something that's sparse.
Yeah, I don't even think you could probably store it on your machine.
Yeah,
Anyway.
okay, that makes sense. Yeah. I get it now.
So I say like just you'd be better off implementing the integration on the DVDCs.
That might be our only choice.
Yep.
I'm gonna ask you a question, Matt. Just circle back to the direct solvers. It's kind of like a anecdotal observation, and I wish John was here, but he experimented a lot with Paradiso, and if I recall, he observed that Paradiso was eventually getting to like a saturation point, where even if you give more threads, it was actually not actually solving the problem faster. I would be curious to know if you experimented with it, or if MUMPS, if MUMPS has the same kind. If you have first, if you observed it, and second, does MUMPS has work around this? Yeah. If that
I
makes
don't
sense.
have.
Go ahead, Thibaut. Sorry.
I was just gonna say personally, I don't have numbers, but I have observed that Paradiso fast, like I think even like things, yeah, like 48 was kind of the maximum thing that was getting, but even before that, like the difference between, for example, 32 to 48 CPUs was minimal. Like it was kind of like an asymptote, and past 48, I had nothing, no gain at all. But that's just a personal observation. I don't have numbers. Sorry, Matt.
Yeah, I have some numbers that I can share here. So this was another benchmark here. So this was, Paradiso and MUMPS. So going from one thread to 32 threads, and we can see that 32 times more threads doesn't mean 32 times faster. It's barely 2 times faster. And then we see a similar kind of saturation here. So going from one thread on this x86-64 to 32 threads, we're not seeing. Actually, I think this was a different benchmark. Let's take a look.
Are those like the factorization times or the actual solves or all of it together?
No, this is okay. This is the same benchmark. I think this was. Let me get you exactly what was timed there. I'm gonna unshare and see what kind of because you don't want to watch me explode the file system.
That would be pretty disappointing if if putting 12 threads is not at least much faster than single thread.
Yeah, here we
Oh,
go.
okay.
This was so this is the what exactly is timed here. So we set up the simulation, and then we run the simulation.
So it's both together. It's everything.
Yeah.
Factor, analyze, factor, and solve.
Yeah. But what we're really looking at here is, the wall times, and going from the MUMPS single thread to the MUMPS 32 thread, and we see, going from, the time about halves. So it's about twice as fast. And it's same thing with Partiso. So that saturation is definitely a thing that happens.
Yeah, it would be
Yeah.
interesting to see if you have a bigger system, right? Because maybe your system is just too small and then there's nothing to work on. But yeah, if you give them something much larger, at what point? It would be good to understand.
Yeah.
like
And
a
for
relation between
those
size.
larger systems, understanding the memory use as well, that's going to be very important.
Yeah, absolutely. Mhm.
Yeah. Whole
A
topic of
lot better profiling capability now than when I first ran these, so it'll be a lot easier to get those numbers.
and the whole topic of sparse solvers is a very interesting thing and how it goes about. It's it's oddly enough, it's all graph theory, how they construct things and how they implement trees, how they follow operations around. It's really fascinating, actually.
A lot of PhDs. For
Yeah,
sure.
a lot of the like parallelization, they break it down into blocks of things. They try to reorder the matrices in such a way that you can work on chunks of things at a time within them. And then even in that case, they sometimes introduce zeros into the blocks to make them blockier. It's really interesting. Like there's a whole bunch of stuff going on. It's fascinating.
I guess one question related to these sparse matrices is, I saw that there was a good while ago, there was an issue discussed in the PyMath solver issue history of looking at the Panua implementation of Partiso, which is significantly diverged from Intel's MKL implementation. The licensing for it looks pretty onerous. But if that's something that could be evaluated, that might be something to understand if it's worth dealing with those kind of licensing situations.
Yeah, because basically Panua Partiso is the licensed Partiso, which is updated every now and then. While I think MKL Partiso, is that like 2004, 2007 implementation? It has not changed since.
So the Panua folks claim that the two implementations diverged in 2006. Looking at the Intel 1 MKL release notes, there have been a couple of comments over the last few years on changes involving the Partiso implementation, but it's been pretty late. So I don't know that the Intel version of it is really actively developed. So we're dealing with pretty old code there.
Yeah, and this one is thread safe, right? We haven't talked about this, but if we could have a thread safe direct solver that could change the way we line things up when we're doing the parallelization at the inverse on the inverse side of things. That being said, you said something, Matt, in the chat that kind of triggered something in mine is the storage of the factorization. If we could reuse the factorizations of the direct solvers, right? Do you have hooks right now to easily save out to disk the solver, the factorization of the solver?
I don't have those hooks implemented, but I was taking a look at the user guide a little bit earlier, and it's a function call to save and it's a function call to restore. So it's not too bad.
Same thing
and
for
if we wanted
Partiso,
to save to a memory map file, you could have some pretty fast serialization.
because then we could instead of having requiring the solver to be thread safe, we could just regenerate them, you know, have mechanism to generate multiple solvers, and then they just reuse whatever has been already be computed, and that would be pretty neat.
Yeah. So one question about the thread safety here is, so I've gone very deep on looking at the solvers, but I have not really, I don't have any familiarity with how SimPEG is sequencing or ordering computations. So one possibility here as well, depending on the sequencing, is there something where we could be doing something where, okay, we factor, and then, you know, we're solving A equals B. Can we make B into a large matrix instead of a vector? And then that could potentially bring in, you know, other BLAS extensions. I was doing some experimentation with the effect of GEMMT open BLAS extension, taking a look at what are the performance differences. It looks like it's only really active when we give a symmetric hint, but I didn't see a really remarkable increase in performance delta between unsymmetric and symmetric, between when GEMMT was available to MUMPS and when it wasn't. But I'm thinking that that might be due to the types of computation that it's doing. If you're doing something that's not really all that parallel, if we could move from, you know, parallelizing, you know, by, you know, giving one instance of MUMPS more stuff to work on at the same time, there might be possibilities there. But I'm not familiar enough to even have a proper informed discussion from my end on SimPEG code.
It is definitely faster if you give, instead of a single calling MUMs or parties with multiple times on a vector, if you give it a matrix, it's definitely going to be faster, all right, to solve. That being said, eventually you're limited memory-wise. You cannot give a B that is too large, because then you have to generate that array, right, before you give it to the solver. Right,
certainly.
So it's kind of, and you know, it would also, if we can parallelize over those solves, that means we could technically cast it over multiple machines, right? So you don't need to do that all at once in one place. We could also spread it around. Yeah,
that would be really nice.
Optimal. Yeah.
And that's something too, where, you know, getting into the types of parallelization that are easy for people to manage. You know, HPC kind of stuff, you know, if you're doing Slurm, job orchestration, and then MPI stuff, like, that's great. If there are things that you can do that are easier to manage, you know, like cloud enabled stuff, you know, if you're going to be running on, you know, I do a lot of AWS work, so, you know, if you can be running on, you know, a Dask cluster, the environment management for that is far easier. And so, broadcasting that, you know, that saved matrix factorization across a cluster is going to be way easier than getting things involved with MPI. Just from the environment management of what software do you have installed on the cluster.
Yeah, and even code-wise, it's much simpler to implement for anyone, right? They can create a new simulation or whatever, and it's kind of a template. It's easier to deploy. That was good. Thank you. I need to get going, but great talk. Thanks, Matt, for the work. Looking forward to see it coming. Try it for sure.
Thanks, Don.
Thanks, everyone. Thanks so much, Matt. I don't know if folks, if anybody wants to stick around, you're welcome to. I also need to drop off, but really appreciate this, Matt. It's super cool to see. And it's great that, you know, you're picking up at this level of the code and making optimizations here. I think it's really exciting. And even, you know, as Joe mentioned, some of the things we can do in the base simulations to just, you know, start to really take advantage of some simple wins. I'm glad you've prompted that. So much appreciated.
Awesome. Yeah, it was great to meet everyone here. I'm excited to do more.
Yes, absolutely. And brainstorm a name.
Thanks a lot, Matt.
Thanks, Matt.
Take care.
Thanks, everyone.
Bye.
Everyone.